So I am Anshul Fai from Department of Mechanical Engineering IIT Bhilai. I will be talking about the void growth amorphous polymers, specifically effects of loading rate on growth. So first of all, regarding the amorphous polymers, I will be mostly talking in a continuum manner, no molecular level things. Okay. So if you look at amorphous polymer, and if you look at the deformation behavior of it, so basically when a strip or when a strip of the amorphous polymer is loaded, initially it shows an elastic response or more or less viscoelastic response. At some point of time, there are shear band appears in these bands and they go to instability region, which shows a yield-like behavior, the way we generally see in metals. And these kind of behavior are kind of intrinsic to these polymers, and they show a softening. And after that, these shear bands expand throughout the length of the strip and almost at a constant rate, which actually gives large deformation to these structures. And after that, when all the polymer chains, when the softening has, when the shear bands have spread throughout the length, basically all the polymeric chains are kind of straightened and they are aligned. And once they are straight, they can no longer stretch, and after that the fracture happens. So this is basically the overall deformation behavior of the amorphous polymers. So these are kind of advantages. They undergo large deformation. They show a yield stress which depends upon temperature, pressure, and strain rate. They show strain softening, which is a kind of intrinsic behavior to that. Rate and temperature dependent hardening behavior after the softening. So some of the examples are polycarbonate, PMMA, polystyrene, etc. As far as engineering is concerned, these materials are important because they show a higher toughness, and because they are loading rate dependent, it has been observed that their toughness is also rate dependent. So they are mostly used in the impact kind of loading conditions. Okay. Now, why wide growth? Because growth and coalescence of microscopic voids are generally precursor to the ductile failure in metals as well as amorphous polymers. So that's why we will look at the void growth analysis. Now, before we go into the simulations of void growth, I would like to show some of the experiments which I have done way back during my PhD. So basically, what we will be looking at, this is a 3-point bend specimen which is generally used for doing the fracture test. What happens? This has a pre-existing crack. It is supported at two ends, and then we apply load at the top so that the crack opens in mode one loading. Okay. So what you will be looking at? We will be looking at a close-up of this crack. Because these materials are transparent, nothing will be visible. But because these crack faces are there, they will be having a. So let me first show the picture. Okay. So what you are seeing here, this is the crack face which is illuminating because of the light. Everything is transparent here because the material itself is transparent and the background is black. Now what we are seeing here, when the loading starts, you can see at somewhere ahead of the crack, these kind of defects start appearing. The material does not immediately fail. The specimen does not immediately fail. There is a accumulation of defect ahead of the crack, and once the defect is sufficient damage has accumulated ahead of the crack, it joins with the main crack and the fracture happens. Okay, so this is a static image of the same thing. So initially you can see this is the crack front, which has no defect ahead of it. At some particular node, a small defect appears at an isolated place. Once the load increases, this defect which was initially there, it starts growing, and another defect appears at some other location, which is again isolated from crack as well as from the initial defect. The same process goes on. Now both of the defects are growing, and another defect appears, and with the growing time, all these defects which are appearing, they join together and form a big defect, which basically forms a big defect, and ultimately it fails. So this is what happens under the static loading. The loading is applied very slowly. Now we did the same experiment at a high speed, that is impact loading. So this is what you see. Again, the same configuration. Only thing as a camera is now looking at a different angle just to observe things. Now this is under the dynamic loading. Here also you can see this image is this phenomena is very fast. I will again show the static loading. So these images are taken at an interval of 1 microsecond. Okay, so again, the same 3-point bend configuration, the only thing is that it is under the impact loading. So initially there is no defect. However, you can see a small defect appearing in front of the crack, and then this defect spreads and connect with the main crack, and the fracture happens. So phenomena remain more or less same. The only thing is in initial case static loading, the void gets the defect has lot of time to accumulate, whereas in dynamic it does not grow bigger. It's very soon it joins with the main crack and failure happens. Okay, so this is the phenomena which actually I analyzed during my PhD, and what we saw with the help of simulations, that the mean stress. So basically, if we consider, so this defect we are seeing in more or less in a two-dimensional area. So we don't know whether this is a void or what kind of shape it has. But since void is a kind of good assumption of any defect in the structure, so we assume that it is a void. And because mean stress or pressure is something which is responsible for generally expansion of voids. So what we looked at into the simulations, we looked at the mean stress at the location where the void is growing, or the location where the mean stress is higher. What we found that with the increase in loading rate, this mean stress which is responsible for defect initiation, that increases. So we saw rate dependent mean stress which is responsible for defect initiation or void growth. At the same time, we also did experiments with different notch radii. So these are the different notch radii we looked at. This is larger, this is smaller than that, this is the smaller, and then there is a sharp crack which is cut through the blade. So by having different notch radius, we can basically vary the trajectory ahead of the crack. And again, when we did the similar kind of experiments, what we found that this mean stress also depends upon what kind of notch radius you are having. So basically, it depends upon the trajectory also, what is there ahead of the crack. So now we found that the mean stress depends upon the loading, mean stress depends upon the trajectory conditions ahead of the crack. So this is one reason where this is one place where the void growth is important, and we have looked at it. Another place where void growth becomes important is basically the polymer blends. Polymer blends are this is an example of PC-ABS blend, which is an immiscible blend. Polycarbonate is one of the polymer. ABS is another polymer which does not mix with the polymer, and it remains there as a particle. Okay, now what happens when these polymer blends are loaded? The ABS again consists of two particles. The one is rubber particle, another is one is rubber particle, another is sand matrix. So when loading happens, this rubber particle actually cavitate at a very low load levels, and they form a hollow sphere. So now this is like a polycarbonate matrix with all voids everywhere. Okay, and these voids now govern what kind of behavior this PC-ABS blend is going to show. So again, if you want to find out if you want to derive the deformation behavior of these kind of blends, we will have to study what the void growth behavior in the polycarbonate. And this PC-ABS is again a material which can sustain very high, which shows very high toughness at higher loading rate. So this is also used at mostly in the higher loading rate configuration. So that's why the effect of loading rate should be observed on the void. Now, effect of trajectory under static loading has already been studied by Steinberg, but we will again look into it. He has done mostly for the small deformation. We will go look into the large deformation case. The effect of loading need to be addressed, which has not been addressed. So what we are going to model, we are going to look at the continuum. Now we have chosen a RV, which is a hexagonal shaped RV, but that can be approximated as a cylindrical RV. And then we considered a void inside it. We will look into different configuration. Now, making it a cylinder helps us in idealizing this cylinder as an axisymmetric object. So instead of doing a three-dimensional simulation, we can basically do a two-dimensional axisymmetric simulation. That is our life. Okay. And then, in order to maintain a constant trajectory, to look into the evolution of void under different kind of trajectory value, we will be applying the stresses, remote stresses or microscopic stresses at a constant ratio, such that we can control the loading condition and characterize what kind of parameters are required. Okay. Now, we will be looking at different parameters throughout the presentation, so I will just define it there. So, macroscopic cost. So, basically, the stresses in x1 and x2 directions, the macroscopic stresses are given as average stresses throughout in that direction, which is denoted as sigma 1 and sigma 2. Macroscopic mean stresses are given as sigma m, which is nothing but the pressure, where sigma 1 plus sigma 2 plus sigma 3 by 3. Remote reactivity, which will be defined as the ratio of mean stress to the von Mises stress, which basically defines whether the component is subjected to more hydrostatic kind of stress or it is subjected to more deviatory kind of stress. Higher the reactivity, higher will be the hydrostatic loading. Lower the reactivity, it will towards the distortion kind of loading. Void volume fraction, we will be looking at how the void volume is growing with respect to the overall cell volume. That is the ratio of this thing. Macroscopic effective strain. Effective strain is again strain. We are converting a two-dimensional strain. This is kind of similar to the von Mises stress corresponding to that. And then applied shear stress. This is something which is there for a non-unvoided section. We will be using it to normalize our plastic strain rates for our voids. Now, in order to simulate this model, we use a constitutive model which is given by Wu and Vandergissen 1996. It depends upon a model given by Boyce in 1998, which was a very simple model, but it can take care of almost all kinds of things: rate and temperature dependence and pressure dependent yield, strain softening, rate and temperature dependent hardening. It can take care of all these things. These are some of the calibration. The model is calibrated against the experimental data for polycarbonate, and rest of the simulation we will be doing only for the polycarbonate. This model has a problem. It can the dots here, the black dots here shows the experimental data of yield stress with respect to strain rate. What does the general behavior shows that up to a certain strain rate it follow a constant slope, and after a certain strain rate under the impact condition it follow another slope. There is a change in slope of the yield stress when at a higher rate. Now, the original model given by Wu and Vandergissen that can only capture a linear behavior at all the strain rates. So, I have modified this constitutive model so that it can capture this kind of bilinear variation of yield stress at all the strain rate, and this model I will be using for my simulations. I am not going into this into the model as of now. Now, the finite element analysis. So, this is my mesh basically. So, the nonlinear constant equation. So, basically, now in order to maintain the constant reactivity, what is basically done, we take a particular node here where we apply a uniaxial loading. Now, this node and this node of the cell is connected with some kind of nonlinear constraint which has been defined by Skog in 1998. These constraints basically convert this uniaxial loading into a biaxial loading or some loading which can maintain the constant stress ratio on this cell, which in order maintains a constant reactivity. Okay. So, basically the cell will be subjected to a loading which will maintain the constant reactivity throughout the loading. Displacement control loading. Displacement of node M governs the deformation of the cell. Now, we will be considering different void size, one small, one medium and one large. Large voids can be, so basically this is a period, this can be considered as a periodic media where this cell is where voids are distributed in a medium. Okay. This is like a periodic boundary condition. We will be considering different reactivity, 1/3 which corresponds to a uniaxial loading, 2/3 corresponds to a biaxial loading, 3, 1, 2, 3, these are the reactivity which you will generally see ahead of the crack or the notches. These are higher reactivities. Applied strain rates, we will be considering a range of strain rates varying from quasi-static to dynamic. We have performed both two simulations. One is static simulation, dynamic simulations. Now, when we say static simulations, even they don't look into consider the inertia effects. Okay, so when we talk about dynamic effects, two kind of effects are coming into picture. One is the effect which is direct, which is coming from the material rate dependence. If your material is strain rate dependent, it will show a higher response at the higher rates. In addition to that, when you consider dynamic conditions, inertia effects also come into picture. So, in general, if you are running a dynamic simulations, both rate effects as well as inertia effects will contribute into the simulation. But in order to quantify them separately, once we run a static simulation where inertia effects are off, in dynamic simulation, inertia effects are on, so that we can kind of quantify both the effects. Now let us first look at the results of static simulation. So these are the three responses of remote mean stress versus the void volume fraction. So we are basically looking at how the mean stress is varying with respect to when a void is growing. So this is normalized void volume fraction with the initial size. Okay, we see basically at all the strain rates we see similar kind of response. With the varying triagility, what we see that with the at a low the void volume fraction, the void growth increases with increase in triagility. The void volume increases more and more as the triagility is higher. If you see a response at some triagility, what happens initially, the void grows very slowly. Okay, after it this linear part actually corresponds to a elastic growth of the void. Then suddenly there is a peak stress, after which the void, so this is a maximum stress, after which it shows an instability. So void grows void grows suddenly to a larger size. For example, if I consider this green color curve, up to this particular point, the void grows very slowly. The F changes almost negligibly. After that, as soon as it reaches this stress, the void will suddenly grow to this particular size, and again it will stop increasing. That means so this is given for the smallest void size which I have considered. Okay, so void grows very small, then it suddenly becomes very large, and again that the growth is again restricted at lower triagility. However, when we go to the higher triagility, the growth is continuous and the void keeps growing. So this restricting void growth is not observed at higher triagility. Now a slightly bigger void, the second size. Now here again the behavior remains same. The only thing you should look at these values with the increasing strain rate, the higher and higher stresses are required, because your material is rate dependent. It response to the material is higher and higher. It requires higher and higher stress to it resist more and more loading. So with the increasing strain rate, higher stresses are required, whereas the characteristics remain same. When we go for a smaller void, when we go for a slightly larger void, what we see, the behavior is still the same. However, the softening becomes more prominent. The softening just after the peak stress become more and more prominent. For a smaller void, these softening were absent in case of the higher triagility, whereas now the softening is even observed at a higher triagility. When we look at the largest void, which is having the highest radius, again the feature is same. The softening has become even more prominent, and now we can see the unstable void growth even in case of the highest triagility. Okay, so whereas again the with respect to strain rate, the response remains same. It requires higher and higher stress. So now what I am interested in, this peak stress, which is basically causing the sudden void expansion, because that will basically determine when the void is expanding in an unstable manner, or at least sudden expansion. So I look at all the peak stresses, and this is the distribution. This is the variation of peak stress for different void sizes with respect to the loading rate. Here the log of loading rate is been plotted. Now what we see that these mean stresses vary up to a certain loading rate, and after that, so mean stress basically increases with the loading rate. And this is what has been observed. This is what was observed in the experiment, that the mean stresses required for void growth are higher at higher strain rates. So this is what we can characterize through these void growth simulations, that at higher loading rate, higher mean stresses are required for sudden void growth. Again, these are for three different void sizes. Now, if we look at so this is in a global sense, we are looking at the mean stress criteria. Now, if we go into the physics of what is happening at the void growth, let us look at individual cases. So this is the lowest triaxility, uniaxial case, slowest loading rate, and smallest void. Okay. Now I look at the situation near the void, at different instances. So as I said, that initial growth is almost linear. So this line shows a linear pattern. So up to this point, void is growing almost elastically. That means if the unloading happens, the void will again come to its original state. If that is also confirmed when you see the equivalent plastic shear strain at the first point, the plastic strain is very small. So it confirms that this growth is almost elastic. Now, when we go to the second point, that is the peak of the main stress, what we see that there is a shear band which is almost at a 45-degree angle, which actually causes the plastic strain in the whole cell. With the increase in loading or with the increase in void size, the shear band actually keeps growing throughout the cell, and the plastic strain starts developing in throughout the cell. Now, when the hardening starts coming into the picture, the plastic strain rate again decreases, and ultimately at 0.5, plastic strain rate is almost zero, or it is basically very small. So basically, the whole cell is now expanding at a constant strain rate, and it actually expands like a unit cell, or kind of a uh, homogeneous plastic strain. That is what we can say, where the void is smaller. Now we look at the same case, lowest reactivity is lowest loading rate, but a larger void. What happens? The same case, the similar is almost situation, but what happens now, because the ligament between the void and the boundary is small, now the again here a 45-degree band is observed, but now the plastic strain is more or less distributed in throughout the cell. That is the only difference what we see when we go for the larger void. Now we look at the condition at highest reactivity. Okay, highest reactivity is slowest loading rate is smallest void. Okay, now here the situation, as soon as the reactivity becomes high, the situation completely changes. Again, this is the initial point where the elastic growth is there, no plastic extended. Now when the plastic extended starts developing, it is now very local. It is not spreading throughout the cell, it is very local near the void. So the whole plastic straining is happening only near the void. The plastic deformation is happening only near the void. With the increase in void, this shear strain rate starts increasing towards the x2 axis, and still it is still locally around the void. There is no shear bands following throughout the specimen. So this kind of transition from this 45-degree shear band to this kind of local plastic straining happens somewhere between the slowest fragility to the highest fragility, and it has been well discussed with the in the earlier work. Okay, I'm not going to discuss that. So at slowest fragility, we see a shear bands going in 45-degree direction, whereas at higher fragility, we see this kind of local plastic deformation. Similar plastic deformation. So this is the larger void. In the larger void, again, what we see the similar kind of local plastic deformation. But now what happens, because this ligament has become small, now this plastic deformations goes across the cell. Okay, because so you can imagine there is a cell along this also, because it's a periodic boundary condition. So now the whole ligament is under plastic deformation, and this plastic strain now grows as a shear band throughout this ligament. And ultimately, this whole ligament actually stretches and it is under a uniaxial deformation. So this kind of, so now you can see this has almost become a straight, initially which was a circular shape, now it has almost become a straight, and this part is now expanding just like a uniaxial specimen. So when the fracture happens, it will probably happen here somewhere. Now, if you look at the plastic strain in all these cases, that this is what we can see. This is the first case which we have seen: smallest void, the smallest void, and the lowest trigidity, uniform plastic deformation. This we have already seen. This is the highest trigidity. Again, very localized plastic deformation, the near the void. This is the large void. Everywhere there is a plastic cushion, non-homogeneous. And this is the plastic cushion only in the ligament, else there is no plastic cushion. So this is the case when at the slowest loading. Okay. Now we go to the dynamic condition. So for the dynamic condition, maintaining a constant trajectory is a problem. So what we do, we only consider three cases where it is easy to maintain the constant trajectory. What are those three cases? Those three cases are uniaxial loading, equibiaxial loading, and hydrostatic loading. In this case, what we do, we maintain we restrict this edge to remain straight and apply the loading in this direction. So this is like a uniaxial loading, periodic boundary condition. This is the second case where we apply the loading in radial direction. Because it's an axisymmetric case, when you are applying the loading here, it means that you are applying the loading in every direction. So this is like a biaxial loading. This edge is maintained to remain straight, so that it is a periodic boundary condition. And then we have the hydrostatic loading, where the loading is same in both the directions. So these are the three conditions which are easy to apply in case of the dynamic conditions. Okay, and at all other nodes we apply initial boundary conditions, so that we can avoid the higher distortion at the initial time stage because of the stress waves. Now, if we compare these results, with the static results, so static simulations. So basically, these are four figures: the two lines and the two dotted lines. What are these results? So the two dots, orange and yellow, they are basically the results from static simulations where the inertia was off. The two lines, dotted and continuous, they are the same simulations at the same strain rates, but the inertia is on. Okay, so what we see there at all triaxiality, what we see that up to a strain rate of 10 power 3 per second, we don't see any difference between the static response and the dynamic response. What does it say? It says that the inertia has not become significant till till a strain rate of 10 power 3 second per second. Okay. However, you can see at a strain rate of 10 power 3 second, you can start seeing some wiggles here, which basically shows that the inertia has started coming into picture, and it shows some wiggles in all the cases. Okay, so we can say that 10 power 3 per second is kind of a boundary where the inertia will start coming into the picture. Okay, this is for one void. I am representing the results. For rest of the voids also, the similar kind of situations are observed. Now, if I look at higher strain rate, so these are the strain rates up to which we don't see any inertia effect. So now we go to a higher strain rate where E dot is equal to 10 power 5 per second. What we see here, again for some void size, what we see that the inertia effects are now becoming significant. So this is a response for uniaxial loading under under uniaxial loading static simulation, that means inertia was off, and this is the response when the inertia is on under the same uniaxial loading. We can see the difference between the static response and the dynamic response. The whole difference is coming only because of inertia, because material rate dependence is already included in this part. Okay, what you can see, the inertia is actually making it difficult for void to grow. It is even making it difficult to grow in the elastic region. In this case, you can see a slope, elastic slope, whereas here you can see the elastic slope is very steep. That means even in the case of elastic growth, the void growth becomes difficult because of the inertia effect. Okay, the same thing you can observe at higher triaxiality, the difference is even higher. This is the biaxial loading static case, this is a biaxial loading dynamic case. You can see the difference is even higher in this case. That means with the increase in triaxiality, the inertia effects are also becoming increasing. They are also becoming large. Okay, so this is what we observe here. Now, if you look at the mechanism of void growth, so here if you see here up to 10 power 3 per second, whether you do a static simulations or dynamic simulation, the void growth phenomena does not change. The void growth shape does not change. Whether it is dynamic condition, static simulation, the most of the mechanism remains same. But since here inertia effects are being introduced, the void growth mechanism will not remain same. So that can be confirmed by looking at the void growth profile. Now here what I am showing is the void growth profile at constant f dot. For example, in this for 1/3, I am looking at the void growth at these 2 points, So this black line shows the initial shape of the void, whereas the blue line and the orange line shows the void growth at 2 successive instances. Now, if you see here, when inertia is not present, void is growing almost in a prolet manner. It makes it kind of a prolet spheroidal. Whereas when the inertia is present, it actually tries to expand it in a more spheroidal like manner compared to what is there in a prolet like manner. That means inertia, it is because inertia is acting in every direction. So basically this growth is more towards like a higher triaxiality case. When we apply a hydrostatic kind of loading, this is how the void tries to grow symmetrically in every direction. So even though the triaxiality is less here, the void is growing in a manner the way it will grow in a high triaxiality loading condition. This is for a biaxial case. Here instead of becoming prolate, it is now becoming an oblate kind of, it is now growing in an oblate kind of manner. Initially this was like this, then the blue line, then it is like orange line. Whereas again, if you see here, it again tries to expand in a more symmetrical manner, more spherical like manner. So this is what is the effect of inertia, which is trying to bring void in a, it is trying to expand the void in a more spheroidal like manner. Now this is at the highest rigidity, which is at the which is kind of a hydrostatic loading. Okay, E dot highest rigidity, highest loading rate. Here you can see I have plotted it for different void sizes. Now these are the three static cases for a smallest void, medium void, largest void. This is what we have seen earlier. These are the three dynamic cases for again for smallest void, larger void, and the largest void. What we can see here, that inertia effects are also amplifying with triaxiality. We have already seen inertia effects amplifying with triaxiality. Here we can see inertia effects are also amplifying with the larger void size. The gap between the orange line, the gap between both the green lines and the gap between both the blue lines actually shows what is the contribution of inertia in growing these voids. So we can see that it is growing with the increasing void size also. So higher the void, difficult will be void to grow, okay, and because of the higher inertia at higher loading rates. So this is what is the overall effect of inertia on the void growth in these amorphous polymers. So in a summary, I can say the effect of material rate dependence on the inertia and inertia effect on the void growth are quantified at higher loading rates. Void growth mechanics remain unchanged in the absence of inertia. So mechanics does not change if inertia is not present. Inertia effects, when become prominent, they stabilizes the void growth. So now if you can see here, earlier the void which was growing instably after the peak stress, now it has become very stable. Now the void growth has become difficult, it has also become stable. It is not growing in an unstable manner. So inertia is basically making the void stable. Inertia promotes a spheroidal like crack growth, the void growth at all triaxialities. So that's all. Acknowledge for the funding from the SCRP DST.
So thank you. Questions and comments or?
That transition where the inertia effects was coming, you have shown one particular value. Is this a case specific or it is?
Yeah, it is. In this case, this is the polymer specific, but because the for more or less all polymers, the density will remain almost constant. I think this will be the kind of density you will see for all. This is the kind of standard you will see for all polymers.
Okay.
You should see.
Okay.
In the first part of the talk, so you mentioned about this this trend rate dependence. So there for this depression or some depression loading and impact loading, like why you didn't change the strain rate of the depression itself, because the geometry was little different, right?
Which case?
Yeah, this one. This is like impact loading,
Right.
and previous one like it was.
Yeah, this is slow loading.
No, but you compared this case with that impact loading.
No, this is just to motivate why the void growth is important. So basically, what we want to understand here is the voids are causing the failure. Voids are kind of precursor to failure. Okay, so this is kind of that. But we actually compared these results, that the mean stresses which are required for defect growth or void growth is basically increases with loading rate.
So these are all impact loading.
These are impact loading. This is slow loading. So you can see this is the rate.
Yeah.
So these are
no. I was wondering that slow loading, that if you keep the same geometry but make it faster and faster, can you like also compare that without like going from
same geometry but
making like that loading rate faster and faster without impact is a different, I think, like it is something is coming and eating probably.
No, basically yeah, so basically that will lie somewhere here. That will lie somewhere here.
It will smoothly connect.
Yeah. So these kind of tests are that they are available, but you will see some kind of connecting between that. Well, most of the contribution comes from the inertia. That's why people look at generally these rates. But yeah, you can up to a certain rate, you will see this is constant. After that, taking it up.
Yeah, you need really high rates. Actually.
Yeah. So these rates are coming from the Hopkinson bar kind of setups.
Other questions? Comments? Well, I have one. I'm just thinking of an old demonstration. You take a plastic bag. So here's where you hold it, and it's been stretched in this way. This is the production direction. So if you cut the strip in this way and this way, if you pull on this strip, then you get this work hardening. You see exactly what you see here. But if you take it the other way, it breaks almost immediately. And that is simply because the polymers have a sort of direction, so that when you push like this, you see this picture. But if you pull in the other way, it breaks immediately. What would that look like in your framework?
That is probably the anisotropy of the polymer. The property is same. If it is isotropic, it should be same in all the directions. The behavior should be same in all directions.
Yeah.
For example, if I take a polycarbonate sheet, if I cut two specimen in two perpendicular direction, I should get the similar kind of behavior.
Yeah. But that's because it's been produced in such a way that it's have any preferred direction. But plastic bags are very anisotropic.
Yeah. So there are two kinds of there are two ways in which a polymer fails. One is basically because of the shear yielding, in which it undergoes a large deformation and fails. And the other way it fails is basically the crazing. So crazing is the phenomena where the crazes appears in the head of the crack. I don't have a picture. So basically the crazes are so if there is a crack, then head of the crack, somewhere head of the crack, there is a damage zone, and it will basically form some kind of breezes here. Yeah. So this is called crazing. So if crazing has come into if you have ever looked up old plastic bottles and all those things, you will see, if you will see in the light, you can see small cracks. Still it has not broken. So those are the crazes which has come. And if the crazes have come in the polymer, it will fail in a brittle manner. So probably that is what is happening when we pull it in the other direction.
Yeah. And then I have another question also, and that pertains to the picture or the slide you showed when you answered your question. Because you see, when you have the notch and you open it up, you see this tongue that sort of comes out. Then it always comes from the center line, the symmetric line.
Yes.
Yeah.
Yes. Yeah.
And yes. And I would have thought, perhaps with a certain lack of intuition, that it should start from the corners, because that's where you get the largest stresses. But clearly it starts in the middle.
No, the middle section is the weaker section. It is ahead of the notch. There the stresses are high.
Yeah. So it's not the corners, because usually it's corners.
Oh, you will along the thickness.
If you take the picture before.
Along the thickness you may.
Yeah, if you go to the picture before, perhaps the other way. Perhaps the other.
Oh, okay, yeah, right. This is first.
That one, yes.
Yeah. In fact,
you see, it starts in the middle.
Yeah, in fact,
Why doesn't it start in the corner?
In fact, this is also coming at the center, somewhere at the center, because in between there is a pain stress condition, and the trigidity is higher in between.
Yeah.
So that is where the chances of growing is higher. That's why it comes at the center. Because towards the surface, it's a plane stress condition. The stresses are zero at the surfaces, whereas inside the material there are stresses in every direction. So it is easy to grow at the center compared to at the surface.
Yeah. Okay. Thank you. Other questions or comments or whatever? Nope. Well, thank you again.